Last time we built one transformer block, attention and MLP and the residual highways that hold them together. One block. Today we build the whole wall. We're going to stack those blocks, bolt on the pieces that turn raw token IDs into next word predictions, and assemble the entire thing into a single class called GPT. By the end, you'll run it once, untrained, knowing nothing, and read a loss number that proves the wiring is correct. Here's the promise. One block was a single brick. A language model is a wall of them. The block we wrote already knows how to talk to itself through attention and think through its MLP. We just need to repeat it, give it a way to read words in, and a way to speak predictions out. Let's trace the full path a sentence takes. Token IDs come in, just integers, one per character or word. We look each one up in a table to get its embedding vector. We add a second vector that says where in the sentence it sits, its position. That sum flows up through every block in the stack. At the top, one final normalization, and then a projection that turns each vector into a score for every possible next token. IDs in, predictions out. Stacking is the easy part, and net sequential makes it almost too easy. We hand it a list of blocks, and it chains them. The output of block 1 is the input of block 2 all the way up. Why stack at all? Depth lets the model build structure on structure. Lower blocks catch letters and word fragments. Higher blocks catch grammar and meaning. Think of it as a column rising. Each floor reasons about what the floor below figured out. At the very top sits the language model head. It's just one linear layer, but it does the most important job in the whole model. It takes each token's final vector and projects it down to one number per item in the vocabulary. 65 characters in our toy dataset means 65 scores. Those scores are the logits, the model's raw opinion about what comes next. And here's the elegant part. The model makes a prediction at every position, not just the last one. Feed it a sequence of length t, and you get back t sets of logits. The shape is bt vocab, b sequences, t positions each, and a full vocab sized opinion at every single one. That's why training is so efficient. One forward pass produces t learning signals per sequence. When we hand the model the true answers, the targets, it computes its own loss right inside forward. We flatten the logits and the targets, so cross entropy can compare them position by position. The predicted distribution against the one correct next token. One number falls out, and that number is everything we're about to spend the next episode driving down. Now the sanity check, and it's a beautiful one. An untrained model has random weights. It has no idea what comes next, so it spreads its guess evenly across all 65 characters. The math says a uniform guess over a vocab of size v gives a loss of ln v. For us, that's ln 65, about 4.17. When we run it and see 441 right in that neighborhood, we know the model isn't broken. It's wired correctly and it knows precisely nothing. That's exactly where we want to start. So the skeleton is complete. About 50,000 parameters, all of them random. It breathes, data flows in, predictions flow out, a loss comes back. But it speaks pure gibberish because it's never seen a word of real text. Next episode we fix that. B0 overview. Let's look at model.py. It's short enough to read end to end, and we'll walk it across 3 clean screens. Page 1 is the imports, the config, and the constructor. Page 2 is the forward pass and the loss. Page 3 is a little main block that builds the model and prints what it sees. Everything you need to assemble a GPT fits on these screens. Up top, the imports and the config. We pull in torch, torch.run, and f for the functional cross entropy. Then we import a block from the file we wrote last episode. No need to redefine it. The little config block names our 5 knobs: vocabulary size, block size, how many positions the model can see at once, the embedding width, the number of blocks, and the number of heads. Here's the constructor, two embedding tables, token emb maps each of the 65 token IDs to a vector of width n EMBD, and pause emb maps each of the block size positions to its own vector. Same width so we can add them. Then the stack itself, we build a Python list of blocks, one per layer, and wrap it in nn.Module sequential so the whole tower behaves like a single module. After the stack, LNF is the final layer norm, and LM head is the linear that projects from any MBD up to vocab size, the head that produces our logits. Now forward, we take token indices IDX of shape, B, T, we look up token embeddings, we look up position embeddings for positions 0 through T, and we add them, broadcasting the positions across the batch. That sum is X, our first real hidden state. X flows through the block stack, then through the final norm, then through the head. Out comes logits, shape, B, T, vocab size, a full prediction at every position. If no targets were given, we return the logits and a none loss, and we're done. But if targets are given, we compute the loss. Cross entropy wants a 2D table of predictions and a 1D vector of answers, so we reshape. Logits become BT vocab and targets become BT. One call to F cross entropy lines up every predicted distribution with its true next token and averages. We return both the logits and that single loss number. Finally, the main block or sanity check. We build the model, count its parameters, make a random batch of token IDs and matching targets, run one forward pass, and print three things: the param count, the logit shape, and the untrained loss. Run it and you'll see roughly 0.05 million parameters, a genuinely tiny model, a logit shape of 4865, and a loss of 441 right next to ln65. The skeleton breathes, but it speaks gibberish. Next episode, we put it in front of real text and watch the loss fall as words start to appear.